For years, neural networks like RNNs and LSTMs faced a rigid physical limit. To read a sentence, they had to process it word by word, following a strictly linear sequence. This linear approach creates a hard computational bottleneck. You cannot compute the 100th word until the 99th is finished. Over long sequences, the system's focus on the present also causes its memory of the opening words to decay. In 2017, the Google Brain team published Attention is All You Need, proposing an architecture that abandoned sequential reading. They designed a system capable of processing all parts of a sequence simultaneously. To understand how a machine tracks syntax without reading in order, we will map the precise mathematical pipeline of the GPT-2 model. We will follow a raw text input as it moves through the architecture to become a 50,257-dimensional probability matrix. Removing the sequential requirement allowed artificial intelligence to scale. By processing data in parallel, these models began digesting massive datasets in a fraction of the time. Computation begins by breaking an input string, like data visualization empowers users, into discrete tokens. These units can represent whole words or subword fragments. GPT-2 evaluates these fragments against a fixed internal dictionary. Its vocabulary consists of exactly 50,257 unique tokens. Each token ID maps to an embedding. Out of this massive vocabulary matrix, the token empowers slides out as a continuous 768-dimensional numerical vector. These 768 dimensions represent learned semantic relationships. During training, the model organizes these vectors so that words sharing contextual meanings group tightly together in vector space. The model treats these dimensions as geometric coordinates, mapping human language into a precise spatial topology. Parallel processing creates a structural problem. Because the transformer ingests all vectors at the same moment, it has no inherent concept of word order. To the raw model, the cat sat on the mat is mathematically identical to the mat sat on the cat. The architecture solves this using positional encoding. Through interleaved sinusoidal functions, the system calculates a specific position marker for every slot in the sequence. The formula applies a sine calculation to the even index dimensions and a cosine calculation to the odd index dimensions. These wave functions generate a unique frequency signature for every absolute position in the text. This positional vector is added directly to the original token embedding, shifting its numerical values to reflect its specific location. Adding a geometric timestamp to the semantic coordinates allows the system to track grammar and sequence while retaining the speed of simultaneous processing. With the tokens embedded and ordered, they enter the self-attention mechanism. Each 768-dimensional vector is multiplied against 3 learned weight matrices, producing a query, key, and value vector. The query acts as an active search input, seeking necessary context. The key acts as an identifying label, waiting to match with an incoming query. The value vector contains the actual semantic content that will be extracted and passed along if the query and key successfully match. This QKV translation reduces abstract linguistic context into an efficient database routing operation. To calculate attention, the model performs a dot product multiplication between one token's query vector and all other key vectors, filling a matrix with numeric scalar scores. Next, a mask overrides the upper triangular half with negative infinity, hiding future tokens. Masking is a requirement for training. It physically prevents the model from peeking at the next token it is attempting to predict. A softmax operation converts the remaining dot product scalars into a probability distribution, where each row sums to 1. The architecture executes this operation across 12 simultaneous attention heads, allowing the network to track grammar, semantics, and tone in parallel. The resulting output matrix is an explicit mathematical map, quantifying the relevance of every word to every other word in the sequence. While attention routes contextual data between the tokens, the multi-layer perceptron, or MLP, refines the representations within each individual token. The first step in the MLP expands the vector's dimensionality from 768 to 3072. This projection exposes deeper patterns. A GALU activation function filters the expanded vector, dictating which subtle patterns pass through and which are muted. A second linear layer compresses the enriched 3072-dimensional vector back to the standard 768 dimensions. This process is wrapped in stabilizers. Layer normalization maintains consistent variance, and residual connections provide a bypass around layers to keep gradients from vanishing. The MLP provides the necessary computational capacity for the model to memorize and process facts independently of the contextual web built by the attention heads. After 12 blocks of processing, the enriched vectors reach the final linear projection layer, mapping the output against the entire 50,257 token vocabulary. This projection assigns raw numerical scores, called logits, to every possible word in the vocabulary, representing their likelihood of being the next token. Before these logits are converted into probabilities, they are scaled by a hyperparameter known as temperature. Low temperature spikes the tallest bars to generate predictable, deterministic text. High temperature flattens the distribution, allowing lower-scoring words a statistical chance to appear. Finally, sampling filters like top K and top P delete the long tail of unlikely words before the final random selection occurs. Text generation occurs as an engineered probabilistic collapse of millions of potential futures into a single specific word. This full sequence, converting tokens to embeddings, injecting time signatures, routing context through matrices, and refining data via MLPs, defines the modern AI pipeline. We have total transparency into the structural mathematics. Every matrix multiplication and activation curve is documented and understood. However, this transparency is limited to the engine's structure. Developers do not know the specific linguistic rules, the 124 million parameters learned during training. The internal logic of those weights remains opaque. The transformer architecture serves as a documented mathematical scaffold that gave rise to an emergent, mysterious intelligence.